This video I want to look at the titration of a weak acid using a strong base to titrate that. So I have not written it in text, but let's just look at it as it would happen in the lab. Let's say we took a 1.25 molarity solution of our sodium hydroxide and we titrated until we got to, let's say, 117.5 milliliters. And we saw a endpoint, and we assume equivalence point, for an unknown weak acid, HF. We don't know its molarity. We put exactly 100 mils of this solution into the Erlenmeyer flask and titrated it with our base. Could we figure out the molarity of that original HF, and could we figure out the pH at equivalence point? Well, yes to both of them. So we know in this reaction between NaOH and HF, let's do the first part. You have to look at how much of the HF you have in moles. So we can say that HF reacts with NaOH in a 1-to-1 ratio to make our water, the strong base, takes the proton from the weak acid, makes water, and we'd get NaF as a salt floating around in solution. Well, we know exactly our titrant, so we can take the 1.25 molarity and times it by the liters. 117.5 is 0.1175 liters, and again we're just using that rule, molarity times volume is going to give us our moles. So I'm going to take my calculator and I'm going to just do that real quickly, and we'll say that we have our 1.25 times the 0.1175. That's going to give us, as far as a mole amount, 0.14, we'll say 69 moles of NaOH that we titrated from the titrant. Now again, if that's the equivalence point, we can say then that the same amount of HF is seen in terms of moles. So this is the first part, is finding the moles of the NaF we make. How do we do that? We find the moles of NaOH we used, 0.1469, and we say at equivalence point it would be equal then. The HF at equivalence point would be 1.1469. Now I apologize, we could stop there if we wanted to know molarity of that original HF solution. We would just divide that by 1, or 0.1, sorry, because we said we had originally 100 mils of this solution. Let's say we took at least 100 mils of that solution and we titrated it. We just divide that mole amount by 0.1, so you get 1.469 molarity. 1.469 molarity. Well, that's kind of easy. We have a second part though. If they ask for what's the pH of this solution at equivalence point, it's not just 7. You would think that if it's strong acid, strong base titration, it would be, but it's not for a weak acid. It's the same case for a weak base being titrated by a strong acid. But we're going to use this in this situation, strong base with a weak acid. Well, we know this. Initially, again, we titrated all the way to endpoint. This has to equal this. We're going to see, though, of course, in a reaction, all of it's driven to the right side by that strong base. So we can just pretty much say minus 0.1469 minus 0.1469 in moles. And we get mole amount of 0.1469 of this NaF. That's how much of that is made, because you didn't have any at the beginning, or there's such a small amount. We now know we have 0.1469 moles of NaF. Okay, second part. So we did our first part of getting to the moles of NaF. Now, because you're near, I guess, a very small amount of hydroxide and hydronium ion in solution at the equivalence point, this little bit can have an impact if some of it goes back to HF. And I need to know how much that is, how much of an impact that has. Because we know at equivalence point, these are really dang low. So that little bit of dissociation back, reacting with just the water that's remaining, that's all we'd have, it can go back and make a little bit of HF and hydronium or hydroxide ion. We got to capture that a little bit. So we can say, well, I know how much we started with, 0.1469 moles of this. I'm going to use moles for now, but we're going to have to get to molarity at the end. And of course, we don't worry about water. And we'd say minus X, because some amount of this goes to the right. It's going to be very small, but we still have to capture it. So our constant for basicity, a constant for basicity, KB, we could write as x squared over, now I'm going to start getting into, I guess, some molarity, 0.1469 minus x all over, well, we added 117.5 mils to 100 mils, so that would be over, if we change it to liters, 0.2175 liters. That would be our molarity value. Well, in this case, we don't have to worry about X. I'm going to tell you why. Because HF, I'm going to box this in, we're going to come back to that later. HF has a Ka of 7.2 times 10 to the minus 4. Using this equation that Kw is equal to Ka times Kb, I was able to find that Kb, if we just plug in that Kw is 10 to the minus 14th, we divide by that 7.2 times 10 to the minus 4th, Kb turns out to be our 1.38 times 10 to the minus 11th. Oh, that's what I needed right there. It's on the very corner of your screen, but it's so important. That means very little of this goes to the right side. What does that mean? I don't have to worry about this little bit of x. I can just rewrite this as 1.38, I'm going to plug in that Kb, times 10 to the minus 11th is equal to x squared over, I'll just do the math, the moles of that NaF, 0.1469, divided by the total volume, I don't think I did that right, 0.1469 divided by 0.2175, we get 0.675, we'll stick with the 4, and from that we can find X. So if we get that, X is going to be the concentration of hydroxide. You say, well, how do I do that? Well, it's just math from this point on, this times this, and just take the square of it. That'll give us the concentration of hydroxide. Once they have that, you're kind of rounding third and going into home, because we wanted to know what was the pH of this solution at equivalence point. Well, we've captured OH. We'd know that because that's equal to X. Well, what we can do then, there's two ways to go at this. You can take the pH of it, you can take the P of that, the negative log of it, plug it into here, and subtract that from 14, and you would find your pH. That's probably the easiest way. Just take the negative log of that value, whatever you get for X. Take the log of it, change it to a negative, put it in this equation, subtract it from 14, and you'd have pH, and you would be done with a pretty dang difficult problem, titration of a weak acid by a strong base, wherein they want to know the pH at equivalence point. That's a little bit harder than just finding what the molarity was of that original weak acid. Bye-bye.